Welcome back to our series on probability theory. I'm Mark Ledbetter. This is lecture video 47, part A, and in this section we're going to discuss the moment generating function distribution techniques for transformations. So this is actually a very easy and efficient method to use. So I hope you're comfortable with moment generating functions by now. In the last section we discussed multiple independent random variables and defined a very important quantity called the random sample. Then we talked about the expected value of some of these key sample quantities, such as expected value of x bar equals mu. X bar is the sample mean, mu is the population mean, and so this makes x bar unbiased. And the same was true for s squared. That is equal to sigma squared. So the sample variance is, the expected value of the sample variance is equal to the population variance. So that makes these both unbiased estimators. We could do for S, the expected value, it's not equal to, in fact, I think I gave that to you, but it's not exactly equal to sigma. So the square root throws everything off a little bit. It's still the best estimator for the sample standard deviation, but that's a topic for next semester. We looked at a theorem for the expected value of the product of functions of a random variable that are independent random variables, and the mean and variance of the linear combination of independent random variables, and did some examples. In this section, 5.4, we're going to look at the MGF transformation theorem and a corollary, and try to get in some examples in this lecture, and then we'll do the rest of this in the following lecture videos. So remember that the moment generating function, or MGF, uniquely defines the distribution. So if two random variables have, so if x has f of x, or has moment generating function, so the moment generating a function of x, if that is equal to the moment generating function of y, then x and y are distributed the same, have the same distribution, or they're identically distributed. The moment generating transformation theorem is given here, so let's talk about that. It's x1 of x2 and xn. If those are independent random variables with moment generating functions, you'll notice that they're not the same. These are not identically distributed here. So m1 of t, m2 of t, up to mn of t. Then the moment generating function of the sum, we'll call that sum of n random variables, s sub n, is equal to, so s sub n is equal to the sum of x1 plus x2 all the way up to xn. The moment generating function of s sub n, forgot the n here, of t, well, we're going to use the definition. So remember that the moment generating function of x is equal to e of e to the t times x. So if I change x here, I need to change it here. So I'm substituting in s sub n, and now I'm going to substitute in what s sub n equals, which is x1 plus x2 all the way up to xn. Now, the next step of this, which I have omitted here, is that I'm going to distribute t across the x's, and that is a very easy, we can all see that we can do that. So e to the tx1 plus tx2 plus tx sub n, and then we can use our knowledge of exponents to break this up into e raised to the tx1 times e raised to the tx2 times, and so forth until we get to tx sub n. Okay? And then we can use our notation to write this as the product of e to the txi, as I goes from 1 to n. So I want to remind you that this is really I equals n on the top. People do get confused about this, and they tend to forget that what we're doing is we're saying I equals 1, then I equals 2, and then up to I equals n. We're taking steps from I equals 1 to I equals n. And so don't forget that that is a value of I. And so when we do that, we have the product. This symbol, the pi, and that's too messy to see, is the product of these. And so because they are independent, we proved a theorem in the last section that I can distribute the expected value across the product by independence of these xi's. And so we end up with our result of this theorem that the MGF of S sub n, which is the sum of the n independent random variables, is the product. So the MGF of that is the product of the MGFs of the individual random variables. Okay, and so that is what we have written here. So that is the result that you'll want to use. And so for the corollary, if x1, xn are IID now, this means that they are identically distributed. Here they were just independent. Now they're going to be independent and identically distributed. And so they only have a moment generating function designated m of t. We don't need the subscript I. And so the moment generating function of S sub n in this case is simply given by S sub n, m of S sub n of t, equals the moment generating function m of t raised to the nth power. Why? Because we take this result from the theorem, and instead of m of I, we have the product I equals 1 to I equals n of m of t, and this is equal to m of t times m of t times ... times m of t, and there are n of these, and they're identical. So this is something times itself n times, that's raised to the nth power. Okay, so that is a sketch of the proof. Let's do an example. Let x1 to xn be independent Poisson random variables with mean and variance lambda I. Find the distribution of S sub n, which is equal to the sum of these independent random variables that are Poisson distributed. Now, if we recall, the MGF of a Poisson random variable x sub I is, since we're going to change lambda I here, we need to use I as a subscript here. M sub I of t is equal to e raised to the lambda I times e to the t minus 1. And I apologize, when we derived this earlier in the semester, the textbook didn't specify it to my memory, and I failed to specify, but this exists for t, any real value of t. Remember, t is continuous even though the random variable x is not. And so this is true for any value of t. So lambda I e to the t minus 1 is the exponent. Now, by the theorem, the MGF transformation theorem, x1 plus x2 up to xn is given by m sub s of n of t is equal to, here's the result that we're just going to use. We don't have to derive it every time. M sub I of t, the product of those, I equals 1 to n. And so we substitute in for m sub I of t here with our e raised to the lambda I times e to the t minus 1. And we can write out this product as e to the lambda 1, e to the t minus 1, e to the lambda 2 times e to the t minus 1, all the way up to lambda e to the lambda n times e to the t minus 1. And we can add the exponents. And so we end up adding the exponents, and then we notice that every one of these has the same, there's no I here, that's not changing, there's no index, e to the t minus 1. So we're going to factor that out. So I've factored that out here, and we're left with lambda 1 plus lambda 2 up to plus lambda n. And I can rewrite this quantity here as the sum of lambda I from I equals 1 to n. I've left off the I equals 1 to n here just because it's so messy, but if you want, you can put it in. Okay. And so this is the MGF of a Poisson random variable with, let's call it lambda star, that's equal to the sum of the lambda i's. So S sub n has a Poisson distribution where we've summed up the lambdas of each of the random variables. We've added them together. Okay? And so this is, remember that this MGF uniquely determines the distribution of S sub n. All right? And so it is in the form of the MGF of a Poisson random variable. Okay? So here's our result that I hope you are making a separate sheet for these results from Chapter 5. We're going to run into several of them, and you will need them handily, especially next semester. So example 2, let's let xi be a gamma distribution, have a gamma distribution with, this is going to be our shape parameter. So this is shape that changes. It's different for each of these. So they're not identically distributed, but they are independent, and they have to be independent for this to work, okay? And beta, this is the same for all of them, and this is the scale parameter. How do you remember which one is which? I don't have it memorized, but I can think of the PDF of the gamma, and I remember there's x to the alpha minus 1. And so if alpha is 1, this is x to the 0, that's a constant, right? And if alpha is 2, then I have x to the 1, which is a line. If alpha is 3, I have x to the square, x squared, which is a parabola. And that's a cubic, and this is a fourth order, and so forth. And so those are different shapes. And so that changes the shape of the distribution. Whereas e to the negative x over beta, beta is changing the scale because it's the e, same base, raised to the negative x over divided by beta. And when you divide by something in the exponent of a natural number e, then you're changing how spread out or clustered the distribution is. Okay, so we want to find the distribution of S sub n, which is the sum of x1 to xn. So the MGF of x sub I is m sub I of t and 1 over 1 minus beta times t raised to the alpha I. This is for m sub I of t, and we said that the alpha is going to be different for each one of these, or could be. And then don't forget the range of t is less than 1 over beta. Okay? And that's going to be the same for all of them, so that makes this easier. Okay? That the range of t is the same for every one. It's not dependent on alpha, so that makes it a much simpler problem. So the MGF of the sum of these random variables is from our product, or from our transformation theorem for the MGF method, is the product of the m sub i's. And so this is m sub I of t. We've just substituted that in for the result of the theorem, and then I can write these, I can expand this and write these out as the products here. And so I've written it out, and you have alpha 1, and notice that the part in parentheses on the bottom is the same for all of these. This doesn't change because it's not dependent upon I. And so we can add the exponents, and that's what we've done here. We've added the exponents, and then we can symbolize these as the sum of alpha I from I equals 1 to I equals n. And so that's what we've done here. And we've done this so that we see what the pattern of this moment generating function is, and we should put that t is still less than 1 over beta. And so this is the moment generating function of a gamma distribution with beta as the scale parameter, and now the shape parameter is the sum of all the individual shape parameters for each of the random variables. Now remember in section 5.2, we showed this result for 2 random variables, that had, and I think I did the specific one where beta was 1, and then the book did one where it has beta is the same. And think about how much easier this method is than the method using the bivariate transformation theorem. And we haven't talked about the multivariate transformation theorem, and we're not going to, but this is the method that we use when we can. Of course, we can't use this method for random variables that don't have a defined or closed form of the moment generating function, such as the beta distribution. Okay? And we see that the Poisson lambda I, the gamma I beta, they're in this class of reproductive family of distributions. Also includes the normal distribution. This is not true for other distributions. So here's your result that you need to write down for this example. Okay. Before we end, also note that this is a very simple problem compared to the one where we let the beta i's change. I have worked out that problem. It's very tedious and challenging to do, and it ends up with a distribution that I had not seen before when I did this. So changing betas, notice that you would also change the range of t for each of these, and so this would be a much more challenging problem. You have to look at the intersection of the different 1 over beta i's to get the range of the new MGF and the new distribution. Okay. So that is going to be enough for this lecture video. So that's the end of this lecture video. Please don't forget to scan and upload your lecture notes before midnight, the date listed in the course calendar. I hope you will take my recommendation to heart and have a separate list of moment generating functions and a separate list of these results so that you can find them quickly for test and homework. If you have questions, please come to virtual office hours. If you can't do that before you need an answer, then by all means email me, but I need you to email me 2 things: a picture of the problem, because I may not have it handy, and a picture of your work so far so I can see how you're approaching the problem, and that will help me help you through email much faster. Please take care of yourself, and we hope to see you next time.